Let's imagine we are at beautiful Hawaii. Under the water, under the sea is the topic that we're going to talk about today, is the U sub. Okay. So U sub stands for U substitution. Okay. Now, how does it work? Okay. Now let's take a look at this example here. We're trying to find this integral here. However, this function over here that we're integrating doesn't match with any function that in the table that we have for integral. Okay, the 13 formula that we have. Okay, so none of them match with this one. Okay, so a method that we can do over here is use U substitution, U sub. Okay, so take a look at this function that we integrate with. Now this expression under the square root is kind of complicated. If that could be a single variable, then this integral will be simpler, right? So how about we let u to be this 1 plus x squared over here? Okay, so we're going to let u equal to 1 plus x squared. Okay, now du dx will be equal to 2x. Okay, now if we're regarding this du dx here as differential, then du is equal to 2x times dx. Okay, now over here, if you take a look here, the 2x dx here actually occurs here in this integral. We have 2x here, dx here. So if we regard the dx here as differential, we can replace this 2x dx over here by du. Okay, in fact, this is actually proven. Okay, the substitution rule actually says that it's permissible to operate with dx and du after the integral sign. Okay, as if they are differential. So it's okay to do that. Okay. So this part over here will become square root of u, and this 2x dx here is going to become du. Okay. Now let's rewrite this square root of u here in power form. Okay. So in power form over here will be u to the 1/2 power, u to the 1/2 power. Okay. Okay. Now we know how to find antiderivative of u to the 1/2 power with respect to u. Okay, the power will say when you take antiderivative, we increase exponent here by 1 and then divide by the exponent, or in other words, times the reciprocal of this exponent. Okay, so this will be that. Okay, now remember we start with this integral that's in terms of x here, right? So at the end we want to return back to x. Okay, so substitute back to x. So we got this right here. Okay, now you can check if this indeed is the right answer right here by differentiate this family of function over here. Indefinite integral corresponding to a family of function where c is any arbitrary constant. So if I differentiate that, okay, then what happened here is the 2/3 is the constant multiple in front. Okay, and then when I differentiate this, then exponent 2/3 will be dropped to the front over here, and then exponent on this 1 plus x squared is going to decrease by 1. So when you differentiate, the exponent is going to decrease by 1. So that is going to become 1/2 power right here. Okay, and well, but that's not all, because we have this inner function 1 plus x squared. So by the chain rule, when we differentiate, we have the times the derivative of this inner function with respect to x. So the derivative of 1 plus x squared with respect to x is 2x. So we have the times 2x here. So simplify, we got the function that we integrate with, which is this function right here. So this indeed is the right answer right there. Okay. Now, as you can see, this U substitution here work. Okay, it's actually proven. Okay. So this is one example of using U sub. That's the substitution rule. Okay, so the substitution rule is a rule for integration. Now we know integration and differentiation are inverse processes. Okay, so we have the substitution rule in integration. What will be the corresponding rule in differentiation over here? Okay, now go back to this. Notice that when you differentiate that, we actually use the chain rule right here. Okay, the chain right here. So in fact, the corresponding rule in differentiation that corresponds to substitution in integration here, it is going to be the chain rule. Okay, so imagine that you have a chain right here. We have this is the chain, and actually pulling this submarine right here. Okay, U sub. So those are the corresponding rule. This is for integration, and this is for differentiation.